Well, hi, Haley.
Hello.
So lonesome in here. What on earth?
It's so weird sometimes. I'm like, how come because this happens to me quite a bit. I will get on Zoom and I'll be here and I'll be the only one there waiting.
You're like, did I do something wrong?
Well, it's just, I don't know why people don't want to go to class.
It's not class, it's recitation.
Okay. Recitation. But
It's a big difference, really. It's a big difference. So I want it to be like a class if you want it to be. I'm happy to go over anything from our list of topics. I'm sort of like through these recitations doing the kinds of things that I would normally do in a lecture section of a class, but attendance isn't mandatory. So it's not class. It's just time for us to talk about course materials. You have those topical videos for everything anyway. So there's no reason you have to show up to these. There's other ways for you to learn the material.
That's understandable.
Which is why not that many people show up. Hi, Renee. Speaking of recitations, I just dropped some of the back recitations from the last few days into our Canvas site. So if you want to rewatch those, you're welcome to. I did have one of those videos that cut itself off after 40 seconds, which totally sucks. So I just hid that one. So that 40 seconds wasn't helpful anyway. But we recovered that material in other recitations, so we didn't really miss anything. So you guys are working through material right now. Any questions that you have come up with as you're working independently? We can talk about those first, or I sort of was thinking about talking through kind of the last half of chapter 5, that kind of stuff, stoichiometry. Renee, what do you think?
Yeah, I haven't. I was out of town the past 2 days, so I didn't. And obviously, I looked this morning, but the past 2 days recitations weren't up. So when I was on last Friday, you were going to start going over chapter 5. So is that what you did? You went over chapter 5?
Yeah.
Yeah.
Monday and Tuesday, really, we've done some stuff in chapter 5.
Okay, so I'll probably have to go over that.
Yeah, the Monday one should be up, if not now, like in 2 minutes or so.
Okay.
The Tuesday one has not dropped yet. It's still processing.
Okay.
So I'll drop that one after class this afternoon sometime.
Okay, awesome. Thank you. Yeah, so I can take notes on what you're going to talk about today, but if you're going to do the end of chapter 5, but
it's really a completely different chapter than the first part of chapter 5. Chapter 5 is really two chapters. All right.
Okay.
Now they're related, but the skills that you learn in the first half of chapter 5 are just sort of like, you don't really need all of those to understand the last half of chapter 5. So one of the things that we've been learning about, and I don't know if you've watched the topical videos from chapter 5, but what we've talked about far are the types of chemical reactions. All right. So there's a short list, like 5 different types of chemical reactions that fit into sort of patterns. You can learn those through those videos. It's pretty easy to learn those. And we've also practiced with how to balance chemical equations. So making sure that in a chemical equation, the number of atoms in the reactants and products are the same, or else we've violated the law of conservation of mass, which means we can't create or destroy atoms in a chemical reaction. All right. So if 8 sodium atoms go into a chemical reaction, they may end up in different compounds in the products than they were in the reactants, but we still have to have 8 sodium atoms that come out of that reaction if 8 went in. So I was going to have you guys practice a little bit with equation balancing. And to do that, I'm going to show you a resource that I've already briefly linked to. So lots of times when I want more resources to practice something, Azul is a great board game, by the way. So I was reading about advanced strategies for that because the couple of times I've played it so far, everybody that I played with has just destroyed me. So I'm trying to learn about how people don't suck at that game so I can figure out what's up with it. Oh, have I not screen shared yet? I guess I haven't, so you can't see my screen. Let's fix that. All right, so I'm going to Google search equation balancing practice. Now, if I wanted to be even more descriptive, oh, come on. Chemical equation balancing practice. All right. And under that, the first couple of links are probably my favorite ones. So this guy has made a huge list of interactive practice problems for you to practice your equation balancing. And then Khan Academy also has one where you can practice balancing chemical equations by entering coefficients, and it'll tell you if you're right or wrong. So let's do a quick one of these quizzes just for a little practice. Hi, Meadow, good to see you.
Hi, sorry, I thought I had the times wrong for recitation today, so I was.
You're fine. I was actually a few minutes late also because my computer wasn't cooperating. I was trying to upload some new content and it wasn't working, so I had to get that working so that it could be working while we're hanging out together. All right. So let's do a short quiz where we try and balance some chemical equations. Remember, when we balance chemical equations, we can't change any chemical formulas. NaCl is always NaCl, but we can change how many of a reactant or a product we have in a reaction. So let's talk through this first one together, and then after that, I'll let you guys do the other four by yourselves. All right. So H2O2 is my reactant, and H2O and O2 are my products. Now, first cool thing about this is this fits into one of those types of reactions that we talked about on Monday and Tuesday. That is a decomposition reaction. All right. If you don't know what that is yet, that means you haven't watched the video from chapter 5 modules, or I haven't posted the 2 videos from this week for our recitations. So you wouldn't have been able to watch those unless you were there. But that is a decomposition reaction. And right now, if I look at the number of hydrogen atoms in the reactants, I see 2 of them. If I look at the number of hydrogen atoms in the products, I also see 2 of them. So that looks fine. I have not created or destroyed any hydrogen atoms in this reaction. Unfortunately, it looks like right now, I have too many oxygens in the products compared to my number of oxygens in the reactants. So how can I equal out my number of oxygens on each side of this equation? Well, first of all, I see an even number of them here, 2, and a total of 4 of them, or 3 of them over here. Now, if I added a coefficient of 2, saying that I made 2 waters instead of 1 water, that would leave me with a total of 4 oxygens on the right and 2 on the left. And I could fix that inequality in the number of oxygens to say I started with 2 H2O2s. So those coefficients, if we multiply the number of atoms in that formula, that gives us a total of 4 hydrogens and 4 oxygens. And then in the products now, we have 4 hydrogens and 1, 2, 3, 4 oxygens. Now, I don't think, most of the time, when you're equation balancing, if there's just one of a product or a reactant, just don't write a coefficient. If there's no coefficient, we assume there's just one of those. So go ahead and try to see if you can balance the remaining 4 chemical equations in this quiz. There's some really good ones here. I'll give you guys another minute before I start putting in answers. I mean, another minute before I put in the answer to number 2. They're pretty fast once you get the hang of them. So after you come up with a set of coefficients, you can always check your work. How many sodium atoms do I have in the reactants here? There are 3 sodiums in Na3PO4. If we have 2 of those formulas, that's a total of 6 sodium atoms. And in the products, I have 6 NaCl's, so 6 sodium atoms in those. A trick that we can use here to balance chemical equations faster is when we have polyatomic ions that are present in both the reactants and the products, instead of balancing individual atoms, we can balance the polyatomic ion as a whole. So in the reactants, for example, I have 2 phosphates. And in the products, I also have 2 phosphates. It looks like I have 3 calcium atoms in the reactants and 3 calcium atoms in the products. And it looks like I have 6 chlorine atoms in the reactants and 6 chlorine atoms in the products. So I haven't created or destroyed any atoms in this chemical reaction. That's a balanced chemical equation. That's probably the hardest one out of all of them. Number 4 is not super easy, but it's not terrible either. Oops. Looks like we're going to need So I did that to balance my number of oxygens and carbons on each side of the equation. So now I have 3 carbons and 6 oxygens on each side of the equation. That also means that to balance my number of irons, I'm going to need 2 of those. So that looks like a good balanced chemical equation to me. Haley, does that not make sense?
No, but that's okay. I have to go finish going through chapter 5, reading quiz stuff.
So the reason why I'm adding these coefficients is just to make sure that the total number of each kind of atom on each side of the equation is equal. Does that make sense?
Yes, but I'll
Okay.
have to, yeah,
So
I get that
let's
part.
talk through how I got to that answer, and it'll help you understand it better so that you can do the next ones. You don't have to be as fast at this as I am. I've been balancing equations since I was 15 years old. That's like 26 years now. Wow. So I've been balancing chemical equations probably longer than most of you guys have been alive. All right. I should be faster at it. That's fine. But the important thing is, like, how do we get to those balanced chemical equations? The basic process is called balancing by inspection, which is basically identify some atom or polyatomic ion that's not balanced in the reaction and add a coefficient to fix it. And then after that, identify another one that's unbalanced and add another coefficient to fix it. All right. So let's talk through that in terms of that third question that we just looked at. All right. What's going on? What? Okay, there we go. So if I were balancing this reaction by inspection, the first thing that I would notice is I have 2 irons in the reactants, 1 iron in the products. I can add a coefficient of 2 to fix that. Now my irons on the 2 sides are balanced. The next thing that I notice is oxygen. I have 4 of those here and only 2 in the products. All right. Now, most of the time, when you have some atom that's in more than one of the reactants or more than one of the products, you want to hold off on balancing that as long as you can. But since carbon is already balanced here, we're going to balance our oxygens. So it looks like 4 total oxygens in the reactants and only 2 in the products. Well, if I do this, that balances my number of oxygens, but it also unbalances my number of carbons. In the end, the only way for us to have both a balanced number of oxygens and a balanced number of carbons, and we would have to keep on going back and forth between the 2 until we got to that point. If we have 3 carbon monoxides, that gives us a total of 6 oxygens. And if we have 3 carbon dioxides, that also gives us a total of 6 oxygens. So balancing oxygen and balancing carbon makes this one kind of a hard equation balance. So in the chapter 5 Alex assignment, the topic that looks like this is called balancing equations with interfering coefficients. And most of the time what that means is you'll change one coefficient and it'll mess something up. You'll fix the thing that it messed up and it messes something else up. You'll fix that thing and it messes something else up. All right. So in the end, you're going to have to do a lot of coefficient changes until you get to a place where they finally equalize. It's a pain in the butt, but that's the way you do it. So let's try another one of these. So if we're going to balance number 4 by inspection, the first thing that I notice is 3 calciums in the reactants, only 1 calcium in the products. So we can fix that by putting a 3 in front of our calcium hydroxide. I notice 2 phosphoruses in the reactants, only 1 phosphorus in the products. I can fix that by putting a 2 in front of pH 3. It looks like now I have a total of 3 oxygens and a total of 12 hydrogens in the products. Oh, wait, is that 3 oxygens? Nope. All right, so I screwed up my balancing here. Now, how many total oxygens do I have in the products here? There are 2 hydroxides in each one of those, and we have 3 of those formulas. So I'm seeing a total of 6 oxygens here and a total of 12 hydrogens. Oh, not a total of 12 hydrogens. That's just OH, not O. So yes, 12 total hydrogens. Why can't I speak today? But the 12 hydrogens are coming from 6 of them in those 6 calcium 6 of them in those 6 hydroxides, and then another 6 of them from our 2 pH3s. So on the right, in total, I have 12 hydrogens and 6 oxygens. That must mean that on the left, I'm going to need 6 waters to balance out hydrogen and oxygen on the 2 sides. All right, so if I total up my number of hydrogens, 12 in the reactants, and then I have 6 hydrogens in our 3 calcium hydroxides, 6 more in my 2 pH3s. That's phosphine, by the way. That molecule was very recently made famous. They talked about phosphine being present in the atmosphere of Venus, and saying that at least the way we know chemistry works, phosphine only ever shows up as a product of metabolism of living organisms. So it's some scant evidence that there may be life on Venus in some respect because phosphine exists there. I think it's more likely because it's a simple binary covalent compound that there's just some chemistry that makes phosphine at high temperatures on Venus that we don't know about yet here on Earth. It doesn't necessarily have to be that something is alive on Venus to make phosphine, although it's possible, I guess. But that's a pretty simple compound to act as like any strong evidence of life on another planet. But anyway, that's where you might have seen phosphine recently, pH3. And then finally, let's look at our last one of these. So zinc, there's one of those in the reactants, so one in the products. That looks balanced right now. Sulfur, one in the reactants, one in the products. That looks balanced right now. And then what about oxygen? All right, that's the fly in our ointment here. So it looks like we have 3 oxygens in the reactants and only, or 3 oxygens in the products and only 2 in the reactants. That's going to be kind of difficult. So let's try and balance our oxygen by adding maybe a 2 in front of O2. Now we have too many oxygens in the reactants. We could balance that out by adding a 2 in front of zinc. So now our oxygens are balanced, but unfortunately, our zinc isn't balanced anymore. All right, so let's balance our zinc by adding a 2 in front of Z and S. Now our zinc is balanced and our oxygens are balanced, but our sulfur is not balanced. This is one of those interfering coefficient things, right? So let's fix the problem that we just created here. Now we've got 2 sulfurs in the reactants and only 1 in the products. Let's fix that problem. Okay, so now zinc is balanced. Now sulfur is balanced. Now oxygen is not balanced because we have only 4 oxygens in the reactants and we have 6 in the products. Finally, by balancing oxygen again, we have balanced everything in that equation. So there is our correct set of coefficients to balance that chemical equation. We did it by inspection, but every time we corrected the balance of one atom, it kept on messing up the balance for another atom. That's very common. That's what we call interfering coefficients, all right? The coefficients are fighting with each other. Haley, is that making more sense as you see how I'm talking through it step by step? Yeah, okay.
I had a quick question for the reading quizzes for chapter 5. They are not showing any due dates yet.
I'll set due dates for those. So I'll have the reading quizzes for chapter 5. I'll split them and have them due next week over the course of the week.
Okay.
I haven't
Yeah.
put the due dates in yet, but they'll be due soon. So there's nothing to say you
Okay,
can't work
so-
on them now and have them due ahead of time or done ahead of time, right?
Yeah.
But they will
Uh-huh.
be due sometime next week. So just keep that in mind.
hmm And then I just wasn't here for the recitation for the lab. Will you post the recitation on like reviewing like the lab tutorial here pretty soon, or or are we just using the one that you did last year?
You can use the one I did last year. Also, I've done quick versions of that tutorial as part of our lectures when we talked about Lewis structures. So in the Lewis structures where we talk about shape, I have used that same program that you're going to use to create the three-dimensional models. I've used that program when I've done that discussion, and I've done all the things that you're going to have to do with it right in those videos already. So I didn't do a separate lab tutorial, but I've used that program. Like I've done the lab tutorial as part of our 2 recitation talks where we talked about shapes of molecules. Okay.
Yeah. And then just use CAM scanner or whatever to submit those from the PDF.
That's right.
Okay.
So in yesterday's recitation, we started talking about this. The last half of chapter 5 is all about one of our central concepts that helps us keep track of mass in chemical reactions. We call it the mole concept. And the mole concept allows us to do that math where we keep track of reactants and products in chemical reactions. We call that kind of math stoichiometry. So if you've ever had a chemistry class before, you maybe learned some stoichiometry. Most of the time, high school chemistry classes do a really bad job of teaching people stoichiometry. And because of that, people think it's really hard. It's not actually hard. We just have to be really sure about this concept that will help us do a good job with stoichiometry. And once you get the hang of it, it's like really easy. All the problems are sort of identical after a while. All right, so what's the mole concept? Let's talk about it for a second. All right, and to do that, we're going to back up just a little bit and talk about a concept in general. We use nicknames to talk about specific size groups of an object. So if we talk about the dozen, you guys all know that means 12 individual objects, 12 individual units of that thing. Does anybody know what a gross of something is? A gross? Hold on a second. My internet is not doing very well right now. So maybe not quite as common as the dozen, but a gross still represents a discrete number of individual objects. It happens to be 144 of them. All right. Now, what I'm going to introduce to you is another term for a grouping of objects. And the term is mole. So 1 gross of donuts is 144 donuts. 1 dozen donuts is 12 donuts. 1 mole of donuts is 6.022 times 10 to the 23rd individual donuts. So why would we have a group that's that big? All right. Dozens or grosses make sense as a group size for fairly large objects like donuts or like giraffes or lions. All right. It makes sense to group them in a small group size like a dozen or a gross. It makes absolutely no sense to group donuts or giraffes in groups of moles because there aren't 6.022 times 10 to the 23rd donuts that have been eaten throughout all of recorded human history. All right? There just haven't been that many donuts. So why would we use such a big group to talk about something? That group size only makes sense if the things that we're grouping are really, really small. Like, for example, individual atoms or molecules. Since they're so tiny, having a very, very large group of them is a decent way to represent them that represents an amount of atoms or molecules that we can normally weigh out in the lab. So that's our first definition for what a mole is. All right, 1 mole of any chemical formula has 6.022 times 10 to the 23rd individual units of that formula. So, a couple of examples. 1 mole of copper has 6.022 times 10 to the 23rd copper atoms in it. So those are the individual units in that formula. It's just copper atoms. 1 mole of water has 6.022 times 10 to the 23rd water molecules, the individual units of water. One mole of magnesium chloride has 6.022 times 10 to the 23rd individual magnesium chlorides. Now, ionic compounds don't have individual units the same way that molecules of covalent compounds work. So we say that there are that many individual formula units of magnesium chloride, which means that there would be 6.022 times 10 to the 23rd magnesium atoms and twice that many chlorine atoms in 1 mole of magnesium chloride. We just can't call these molecules because there's no such thing as one discrete piece that has a magnesium atom and 2 chlorine atoms anyplace. So that's our first definition. That allows us to connect moles, this grouping, to an individual number of atoms or formulas. Second definition is something that allows us to connect that to something that we could actually read or on a scale in the laboratory. For any chemical formula, one mole of that formula is equal to the total when we add up all the average atomic masses in that formula in units of grams. So what does that mean? Where's my periodic table? I only have like 10 of them and they're never around when I need them. Imagine that we had 1 mole of, gotta zoom out. Imagine that we had 1 mole of zinc. Zinc, the chemical formula for zinc is just Zn. So if we add up all of the average atomic masses in that formula, we just have the mass of 1 zinc, which is 65.39. So in units of grams, that's 65.39 grams of zinc. That tells us exactly how many grams of that formula there are in every 1 mole of that formula. One mole of boron would have a mass of 10.81 grams of boron. Now, what if we had a chemical formula that had more than 1 atom in it? So, for example, what if we had 1 mole of CH4? In order to figure out how many grams there were in 1 mole of that formula, we would have to add up all the atomic masses in that formula. So we have a carbon and 4 hydrogens. So the total of all of those average atomic masses together is 16.05. That tells us that there are 16.05 grams of CH4 in every 1 mole of CH4. So why don't you guys try? How many grams are there in 1 mole of chlorine gas? Cl2 is the formula for chlorine gas. So adding up the atomic masses of those two chlorines, 35.45 times 2, gives us 70.90 grams of chlorine in every 1 mole of chlorine. Now, what's really cool is if we use these two definitions together, we can come up with some really interesting ideas that we wouldn't expect, okay? So, for example, I'm looking around for an everyday object that is elemental or close to elemental here. So I don't have it in front of me, but down in my garage, I have some spools of copper wire, pure copper, all right? So if I have 1 gram of pure copper wire, how many moles of copper are there in that 1 gram of copper wire? And how many copper atoms do I have? This is really cool because if we were actually in the laboratory, we could very easily spool out 1 gram of copper wire and weigh it on our lab balances, all right? That's something we could hold in the palm of our hand. So using this mole concept, we can actually calculate to a number of significant figures the actual number of copper atoms that are in that wire. It's going to be a huge number, but we can calculate it pretty easily, actually. So how do we do that? All right, we got a gram of copper wire. How many moles of copper do we have? How many copper atoms do we have? So first, let's look for copper on the periodic table. I see it right here. Its average atomic mass is 63.55 grams. Now, what two definitions have we learned about in terms of what a mole means? We know that 1 mole of any chemical formula has 6.022 times 10 to the 23rd individual units of that formula. So if we're talking about moles of copper, that means that in every 1 mole of copper, there are 6.022 times 10 to the 23rd copper atoms in that. The other definition we know is based on any chemical formula, how many grams there are in 1 mole of that formula. We get that by adding up all of the average atomic masses in that formula. So since copper just has Cu in its formula, if we look at its average atomic mass, that tells us that there are 63.55 grams of copper in every 1 mole of copper. Those are conversion factors, right? 1 mole of copper is exactly the same size as 63.55 grams of copper. 1 mole of copper has exactly 6.022 times 10 to the 23rd individual copper atoms in it, at least to 4 significant figures. So if we start out with 1 gram of copper, the amount of wire that we weighed out on our lab balance, we could figure out how many moles we had by using that second conversion factor. So if we wanted to convert our grams of copper into moles of copper, how would that conversion factor look? It would have to have moles of copper in the numerator and grams of copper in the denominator in order to get my units to cancel. Does that make sense? So right from our definition of what a mole of any chemical formula is, we see that every 1 mole of copper has a mass of 63.55 grams. And our grams of copper cancel, and we're left with a number of moles of copper for our answer. And to 3 sig figs anyway, I'm getting 0.0157 moles of copper. Now, how would I convert that into a number of individual copper atoms? We can use this other conversion factor to convert from a number of moles of copper into a number of copper atoms. So when I actually did the calculation, I got 2 more decimal places worth of information. I'm not going to round until the very end here. So this is my answer with the correct number of sig figs, but if I carry that calculation through, I'm going to carry all my decimal places through and then round at the very end when I get to a number of copper atoms. So if that's my number of moles of copper, we know that every 1 mole of copper has 6.022 times 10 to the 23rd copper atoms in it. So my moles of copper cancel, and I'm left with a number of copper atoms. So rounded to 3 significant figures, because I started with 3 sig figs for my mass, I'm calculating that that 1 gram of copper wire has 9.48 times 10 to the 21st copper atoms in it. So with a simple 2-step calculation, we started with a mass of copper that we weighed out on a lab scale, and we've been able to figure out how many copper atoms there were in that piece of wire. That's pretty awesome. So let's try going the opposite direction now. You can use your own periodic table. I know that I have a silver ingot that contains 7.75 times 10 to the 26th individual silver atoms. So how much does the ingot weigh in grams? If we start out with silver atoms, we should be able to convert to moles of silver. And from moles of silver, we should be able to convert to grams of silver. See if you can do that using your conversion factors that convert between moles and grams and convert between moles and atoms. All right, let's try it. So first, we're going to need to convert those silver atoms into moles of silver. And we know that 1 mole of any kind of atoms has 6.022 times 10 to the 23rd individual atoms in it. To convert to grams, we need to look on the periodic table where we see that 107.87 grams is equivalent to 1 mole of silver. One mole of silver has 107.87 grams of silver in it. So using those two conversion factors, my atoms of silver cancel, my moles of silver cancel, and I'm left with grams of silver. So let's do the math and see how many grams is that ingot. So it looks like I'm getting 138,869 grams. You guys get the same thing? Renee, yes, that's a yes. Okay. So that's an awfully big ingot. $139 kilograms of silver. So like about 300 pounds of silver in that ingot. That's a big ingot. But possible. We could, I'm certain at some point somebody has smelted an ingot larger than 300 pounds of silver. That'd be worth a pretty penny. Since my wife makes jewelry, one of the things that I like to do is at estate sales, look for sterling silver pieces that are really cheap so that we have something to use to melt down for making jewelry with. And recently I found an antique crumb duster. Imagine like a small dustpan made of pure silver. Well, made of sterling silver, which is like 91% silver. So I found one of those and it was marked $1 at the estate sale. It was half a pound of silver and I got it for $1. Pretty awesome. Not quite as good as 300 pounds of silver, but decent. So the key here is that the concept of the mole connects something that we can see. All right. So we could weigh out an ingot of silver that was this big. It would take a really big scale to do it, but we could do it. To a number of individual atoms. That mole concept connects what we can see or weigh out to a number of individual atoms or individual molecules that we could never count, even if we had eternity to count it. Now, that also allows us to keep careful track of masses in chemical reactions. Let me show you how that works. So we're going to look at a very, very simple chemical reaction. Actually, let's go even simpler than this. So this is a decomposition reaction. Carbon dioxide under the right conditions will decompose into carbon monoxide and O2. Decomposition is where we have bigger, more complex things that break apart into more smaller things. Okay, so why have I written this? When I look at this equation, I can read it a couple of different ways. All right. In this, in those two CO2s, there are two individual CO2 molecules decomposing to make two individual carbon monoxide molecules and one molecule of O2. That's one way that we can read this chemical equation. So a key here is that we can read chemical reactions in terms of numbers of moles of reactants and products also. So these coefficients can be talking about individual units, or they can be talking about groups that are all the same size. So we could also read this chemical equation: 2 moles of carbon dioxide make 2 moles of carbon monoxide and 1 mole of O2. Why is that useful for us? It's useful because since we now know how to convert between grams and moles for any chemical formula, that means if we know how many grams of carbon dioxide we put into this reaction, we should be able to calculate how many grams of O2 it should make. Because for every 1 mole of CO2 that we put into this reaction, we get out 1 mole of O2. All right. This new way of us reading this balanced chemical equation is a way that's going to let us do a lot of really interesting math that keeps track of masses going into and coming out of the reaction. So,
Dr. Musk.
yes.
So I'm lost with the how does 2 individual CO2 molecules make 2 individual CO molecules plus 1 O2 molecule? Doesn't that give you too many O's?
Nope.
Oh,
I see 4 oxygens on the left and a total of 4 oxygens on the right.
Oh, I see. Okay. You're not saying, okay, I understand. Sorry.
Does that make sense?
Yeah. Thank you.
Yep. So the key here is that we can read these coefficients in the balanced equation in terms of like individual molecules, or we can read them in terms of moles of reactants and products. So a mole is just a group of molecules or atoms that's always the same size. So if there are 2 CO2 molecules going in and 1 molecule of O2 coming out, then there have to be 2 moles of CO2 going in for every 1 mole of O2 going out. That's the same ratio. All right. So this reading where we think of those coefficients in the balanced equation as numbers of moles really lets us do some interesting math with chemical reactions. So if I decompose 10 grams of CO2, how many grams of O2 would I make? I know how much CO2 I'm putting into this reaction. How much O2 in grams am I getting out? Here's how we solve this problem. If I start with a number of grams of CO2, using our definition, we should be able to convert to a number of moles of CO2. Now, how does that help us? Because this balanced equation tells us if we put 2 moles of CO2 in, we get out 1 mole of O2. In other words, that's a conversion factor. that allows us to convert from a number of moles of a reactant into a number of moles of a product. So if we know how many moles of CO2 we're putting in, we can convert to a number of moles of O2 that we're getting out of the reaction. And if we know how many moles of O2 we make in the reaction, we can use our definition for how many grams there are in a mole of any chemical formula to convert to a number of grams of O2. So before you do this calculation, think about what you would expect the answer to be. All right, if I start with 10 grams of CO2 and it decomposes, the mass of O2 that I should end up with should be something less than 10 grams, right? Because not all the mass in my products is going to be O2. Some of it is going to be that carbon monoxide. Now, if I totaled up the mass of carbon monoxide and the mass of O2 that I get out of this reaction, that should equal 10.0 grams, because mass can't be created or destroyed in a chemical reaction. But we're just worried about how many grams of this product, the O2 that we're making. And we know that that has to be something less than the total mass that we started with, 10.0 grams. So how do we convert that into a number of moles of CO2? Well, we have to add up all the atomic masses in that formula. So 12.01 for carbon, and then 16 for each of my oxygens. So 32 plus 12.01 gives me 44.01 grams of CO2 in every 1 mole of CO2. So I got that number by just adding up all the atomic masses in that formula. To convert from moles of CO2, the reactant, into moles of O2, the product, we can use our conversion factor, which is the coefficients in that balanced equation. So the balanced equation tells us for every 2 moles of CO2 that we put in, we get out 1 mole of O2. And finally, if we add up the atomic masses of those 2 oxygens, we will realize that every 1 mole of O2 has a mass of 32.00 grams. So if you put this into your calculator, you should end up with some mass of O2 that is less than 10 grams. So I'm getting 3.64 grams of O2 coming out of this reaction. Congratulations, we have just done our first real stoichiometry. All right, stoichiometry is the math that allows us to calculate how much of a product we would expect if we know how much of a reactant we're putting into a reaction. Now we can also do it the other way. Let's say that I wanted to use this reaction to make 100 grams of O2. I could also calculate how many grams of CO2 I would need to start with to make that happen. So let's do that. If I wanted to make 100 grams of O2 with that reaction, how many grams of CO2 would I need to use? Very, very similar thought process here. If we're starting with a number of grams of O2, we can convert into a number of moles of O2. And using the coefficients from the balanced equation, we should be able to convert back into a number of moles of CO2. And then using our definition for converting from moles to grams or grams to moles, we should be able to convert back into a number of grams of CO2. So this is stoichiometry, either trying to predict how much of a product we get out of a reaction or doing the calculation to see how much of our reactant we need to use to get a certain amount of product out of a reaction. It's very practical math. Lots of times when we do chemistry, we have a specific amount of a product in mind. And in this case, we can do calculations to figure out how much of our reactants we need to make that amount of product. Renee, you're the only one left.
Sorry, I'm taking a call from my son, but I'm watching what you're doing.
It's totally fine. I just looked down for a second and was answering a student question via text. And I looked up and everybody else is gone except you. Goodbye, Meadow. Have a good afternoon.
I'm still lost as well, but it's okay. I'm going to go back and catch up and figure it out.
This is really hard. So Renee, if this is like not making any sense at all, go back and look at what those two definitions for what a mole is.
Yeah.
That conversion factor is the conversion factor that lets us do all of this interesting math with chemical reactions.
Yeah.
So what we have to realize is that those coefficients in a balanced equation, 2, 2, and 1, represent numbers of moles of reactants and products. And since we know how to convert between moles and grams now, we can figure out how many grams of a product we get given a number of grams of a reactant. That's stoichiometry.
Right.
All right. So there are definitely lots more examples. Go ahead.
You're really methodical in how you lay things out. I just need to go back and check, like get caught up.
And I do that on purpose because thinking about how your units cancel and thinking about what conversion factors you're going to use, that's the way to get really good at stoichiometry. All right.
Yeah, it's super
So
helpful
most of the time, the conversion factors that we use when we're doing stoichiometry with balanced chemical equations, oh, you didn't see that one? Balanced chemical equations, really we're most of the time just converting between grams and moles of different chemical formulas.
Yeah.
All right. We also use the coefficients themselves as conversion factors. So in this step right here, to convert from moles of O2 into moles of CO2, we're going to have to use the conversion factor that we make 1 mole of O2 for every 2 moles of CO2 that we put into the reaction. That's a conversion factor. All right, so let's set this up. We start with 100 grams of O2. Now, in order to convert that into moles, we have to add up all the atoms in that chemical formula, their atomic masses, which gives us in every 1 mole of O2, 32.00 grams of O2. Do you know where that number comes from, Renee?
No.
Okay.
Oh, yes, I do. It's from the periodic table.
Exactly. So there are 2 oxygens in that formula. Each one of them has an average atomic mass of 16. So 2 of them is 32.00. That is the number of grams in every 1 mole of that formula. All right. So for any chemical formula, we add up all the atomic masses, and it's that many grams in 1 mole of that stuff. Okay. Now, since I'm asking how many grams of CO2 I would need to use, we have to have some way to convert these moles of O2 into moles of the reactant, CO2. Well, the balanced chemical equation tells us that for every 1 mole of O2 that we get out of the reaction, we have to put 2 moles of CO2 into the reaction. That's how we get that conversion factor to work, right from the balanced equation. For every 1 mole of O2 we get out, we got to put 2 moles of CO2 in. And then finally, to convert to grams of O2, we just have to add up all of the atomic masses in CO2, and that tells us how many grams there are in every 1 mole of that stuff. So carbon is 12.01, each of the oxygens is 16.00. That gives us a total of 44.01 grams of CO2 in every 1 mole of CO2. So it looks like our grams of O2 are going to cancel, and our moles of O2 are going to cancel, and our moles of CO2 are going to cancel, and the units we have left are grams of CO2. That's what we wanted. We wanted to figure out how many grams of CO2 would we need to make 100 grams of O2. Note that if you're thinking about what answer to expect here, you should expect an answer more than 100 grams, right? We're going to need more than 100 grams of CO2 to make 100 grams of O2. So I'm getting 275 grams of CO2. Did you get the same thing?
Yes.
Yeah.
So you're just rounding to the nearest whole number in this case? Oh, is it because it's
No. I should have rounded to 4 sig figs instead of 3 because I gave you 4. I've already turned my calculator off and closed it, but I should have given 4 sig figs there, not 3.
Okay.
Sorry about that.
It's 0.06, so just be 0.1, right?
Yep.
Okay.
Apologies.
I just wanted to make sure.
Sig figs are really important.
that.
Sometimes just in the interest of being fast, I forget to do them correctly because we're like super out of time right now. I've got office hours in 9 minutes.
Oh, okay.
No, it's totally fine, but I just didn't want to keep you past like an hour and 20 minutes, which is like the longest I ever want these to go.
Oh yeah, I didn't realize what time it is. Okay. Thank you.
You're welcome. And if this is not making sense yet, watch the videos from the last half of chapter 5 for 1, and 2, we're going to do a lot more examples like this in recitation, at least for like the next 2 recitations. It'll be nothing but doing stoichiometry problems. This is really hard. It's something that students struggle with. And the other thing I'll tell you is the chapter 5 Alex assignment is really long because these kinds of problems are hard. So start working on it early rather than late to make sure you have enough time to finish it.
Yeah, good advice. Okay, thanks.
You're welcome. Okay, I'll see you hopefully tomorrow night, but if not, then sometime soon.
Yeah, I'll be here tomorrow night. Thanks.
Sweet.
Okay,
You're
bye.
welcome. Bye.